to learn something about turbulence. Now, can you please confirm that you can hear me just by typing yes? Good, that is nice. So, welcome. Today we need to look into some mathematical background, some mathematical concepts that are very important and useful for the further lecture. Because we are about describing turbulence, we want to develop programs for the computer, and these need a mathematical foundation. The calculations require some useful equations, some suitable equations. These equations tend to look quite complicated, and we need a simple notation for them. We also need to think a little bit about statistics. I'm not doing a formal introduction into statistics, but I'll present a few quantities to you, describe what they are, and you can think more about them or look them up if you do not understand the details sufficiently from my brief introduction. Okay? So, first, one thing. We need the so-called index notation for vector equations. Here you can see the Navier-Stokes equation in index notation. Please note that you have the vector u here with a little index I. Here you have the same velocity u again, but you have it with an index j. So effectively, these are the same vectors, but they have some different calculation rules. We will elaborate a little bit on them, but I would like to ask you who has seen this type of notation before. I will start a little poll. You see? I need to change my screen a bit for doing that. Okay. So, please answer now. Who has seen this notation before? Who knows it? Yeah? Yes means yes, you have seen this notation. No means you have never seen it before. You don't know what it is. I have answers now from half of the class. I'm still waiting for the other half. So, have you seen this type of notation or not? Yes, you've seen it. No, you have not seen it. I'm still waiting for about 8 or 9 answers. You may have to allow for the displaying the sidebar. You may have to enable this on your computer. On the left-hand side, where you can also see the chat. Okay, I still only have 14 answers, so about 10 people haven't answered yet. Good. Let's stop here. So it's fairly clear that most of you have seen this notation. For the other ones who haven't seen it yet, I will do a quick repetition and a quick revision. And this may also be good for those of you who have seen it. So this is a notation to write the entire Navier-Stokes equations. You will not see any tensor symbols or vector symbols in the way that you may be more familiar with them. So nothing like a vector v or a tensor t, or maybe bold print v or bold print t. Nothing like this. This is a notation that only works in Cartesian coordinates, but there it's very convenient. One advantage is that if you write a vector u, not as vector u, but you write it as ui, that it becomes very easy to program for a computer, because I runs from 1 to 2, 3. So u1 would be the first component, u2 would be the second component, u3 would be the third component of the vector. One advantage of the index notation is that it's very easy to translate this into a computer program. So here we have an expression to calculate the change in momentum. Rho u might be a computer program calculating the rho times u, so momentum. And this has different components. It would have 3 components. So you have a field depending on x, y, and z for the x component, for the y component and z component, or in other words, for the first, second, and third components. And now you can just loop through these components like this. So index notation is a very natural notation if you want to move things on a computer. And with turbulence, we want to move things on the computer. Now, let's move on. Index notation is also less prone to errors, and it's a much more compact way of writing equations, because this is an equation that you can memorize. You can also memorize the tensor notation, but when you use tensor or vector notation, you have to remember all the vector rules, all the vector products, all the type of matrix products, and all the differential operators. And with index notation, it's very easy to memorize this and to just calculate, as you will see later. One more question, tensors. Which type of tensors do we need? Obviously, a tensor of rank 0 is a scalar, so it's only a magnitude. For example, the temperature T that we have here. A tensor of rank 1 would be a vector. It has a magnitude, but it also has a direction, so it's not unidirectional. One example would be the velocity vector x, v, or the location vector of a point x. And now the question may be, are tensors of rank 2 or even higher useful? Well, we all know the stress tensors. Stress tensors do have 9 components. All stress tensors are symmetric. So please remember that a stress tensor is always symmetric. That means it's diagonal, has values, and the off diagonals, so the upper triangle and the lower triangle, have symmetric values, meaning these values here are the same, these are the same, and these. You all know that, but I wanted to remind you because this will be quite important when dealing with stress tensors. Now you may wonder, are tensors that are even higher than second order also useful? And I can tell you, yes, they are quite useful, and actually they are quite commonly used. They are used in turbulence theory. We'll see a third order tensor quite frequently. Sometimes we'll even see fourth order tensors. Don't worry, we do not have to deal too much with them because our theories will always simplify them away, or if we can't simplify them away, we'll neglect them for a very good reason, as you will see later. But they have a meaning, they exist, and they're useful. Quick reminder about the stress tensor. A stress tensor has 3 rows, 3 columns. The notation, if we do an index notation, as sigma I j has 2 indices. It has the index I and the index j. The index I is the first index in this very case, and the first index gives the cutting plane on which we would discuss the stresses. So if we have a stress sigma 2 j, then we look at this cutting plane, something that is normal to the second direction, and look at the stresses on the surface. And the directions of the stress on this surface are given by the second index j. So here, the 2 gives the direction of the force in the 2 direction. The index 1 gives the direction of the force or the stress in 1 direction, and 3 in 3 direction. So in this very case, sigma 2 would be a tension, and the other ones, sigma 2 and sigma 2 would be shear stresses. You all know that, but I wanted to remind you of that. Now let's have a look at the index notation and introduce it a bit more generally. So we use 1 Latin character as an index, I, J, K, L, M, N. If you run out of letters there, you can still use more letters. So we have something that is a UI. UI means it's a vector, U, with 3 components. So the convention for index notation is normally that a vector has 3 components like 3-dimensional space. We have U1, this is the first velocity component. We have U2, or we have U3. If we were to do a normal vector notation, we would probably call the first component lowercase u, the second component of the velocity vector lowercase v, and the third component w. So in other words, with index notation, we have the following thing. We have ui equals u1, u2, u3. again, certainly similar to U, V, W equals vector U in vector notation. Okay? The same applies for the location vector xj. Here we would use x1 instead of the component x, x2 instead of the component y, and x3 instead of the component z. And here again, bear in mind, it always makes it easier to program things on the computer. So, and this is the most basic part so far. Any questions? If you have any questions or want to ask a question, please type it into the chat window. I'm just looking at the chat window to see if something pops up there. That's clear so far. All right. Then let's move on. We can certainly use this also to write derivatives, differentials, and so on. So here, we have a partial derivative with respect to xk. So the quantity that will be derived is not given. It's just the operator del over del xk. And this is del x1 as the first component. The second component of this guy is del x2. And the third component is del x3. So this expression here is already a vector by itself. And to summarize things, here in our example, ui or uj, they are velocity vectors. And they are the same velocity vectors, but we still can use different indices to refer to the same vector for reasons that you will see later on. I, xj, or xk are the components of the vector x. Now, in some cases, we may end up with two different letters, as I told you already. So here in this case, ui, uj, we have an index I and an index j. The vector ui is the same vector as the index oj, but we apply different calculation tools because ui and uj is something that has always two indices. And if you think about a mathematical construct with two indices, or anything in general, you end up with a table. A table has rows and columns. A matrix has rows and columns. A matrix requires a first and a second index. What we have here is a tensors of second order. And in this case, it's just the product of the vectors. And obviously, the components can be u1, 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 u2, if we look at j equals 2, and u1, u3 for j equals 3. If we increase I to 2, we end up with the u2 row, this one here, with u2, u1 for j equals 1, and so on and so on. So here we have created a tensor. What you see here is the product of two vectors. We can also describe second order tensors directly. So we can have something like uppercase phi ij, or probably better known and more familiar, sigma ij, being our familiar stress tensor. So here we can have something like phi 11, phi 12, phi 13. So here you can see the direct tensor directly. So here phi or sigma are tensors, whereas up here u, both u's are just vectors, but the product is a tensor. And down here we have the gradient of the velocity ui xj, and this, in this case, is certainly a matrix. So the gradient of a vector field becomes a matrix, and here we have del u1 del x1, del u1 del x2, del u1 del x3, del u2 del x2, and so on. Now, since this is very important for the further class, any questions? Okay. Now here sitting at my computer screen, it's actually quite nice to speak in a low voice, not very loud. Can you all hear me well and clear, or would it be better if I spoke a little bit more loudly? Do I need to speak up, or is it fine? Okay, cool. This should change later on because of some background noise. Let me know. Please type into the chat window or please speak up. Okay, thank you. Thank you. Right, let's move on to the notation of vectors and tensors. So we can obviously extend this to 3 Latin characters. Here we have a UI, UJ, UK. We are going to see some constructs a few times during the turbulence class, but we are actually not going to do too much about them. We'll acknowledge them, but most of the time they will disappear fairly quickly. So this is the product of 3 vectors, UI, with these components, UI1, U1, 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 and then the next one would be U1, U1, U2, and so on. And you can go all the way up through all the rows and columns and probably layers to get at the component U3, U3, and U3. And if you think of this as a tensor, this is obviously a 3rd order tensor. So I like to visualize this as essentially 3 matrices stacked up on each other. It will look a little bit like one of these magic cubes of Rubik's that can quite tire you out if you're trying to resort them again. You have 3 rows, 3 columns, and 3 layers. Now we come to a very important concept, and this is something to memorize. And this is actually the reason for the great power of this index notation. This is the Einstein convention, Einstein's convention of summation. Let's have a look here. Here, what is written is UI, UI. We have the same vector twice, but this time we have the same indices. And now the rule is if we have the same index twice, so not UI, UJ, not UI, UK, but UI, UI, or UJ, UJ, or UK, UK, then we take the sum instead of treating the components as individual components. So then we do not have the components U1, U1, or the component U2, U2, or the component U3, U3, but we actually have the sum of them. U1, U1 plus U2, U2 plus U3, U3. And if you write this down in a classical format, this would be UI, UI, UI times, 1, 2, 3, 1, 2, 3, giving us dot product U1, U1 plus U2, U2 plus U3, U3. So this would be the dot product of these vectors. So what you see here is that the index notation just very conveniently and easily gives us the dot product of 2 vectors through this Einstein convention of summation. So this here corresponds to vector U dot vector U. That's cool, because it simplifies the calculation rules a lot for us. If we have a tensor phi, and we use phi jj, then we end up with phi 11 plus phi 22 plus phi 33. So what this is mathematically is the trace of the tensor, or in German die Spur des Tensors, also die Liste der diagonalen Elemente. This is the sum of the elements on the diagonal of a matrix. And we can also apply this Einstein rule of summation to other operators. So in this case, we have a del UK, del xk. So we have a velocity field and we look at its gradient. But this time, we do not look at its gradient, but we do look at something else, because we end up with del ui xi plus del u2 x2 plus del u3 x3. So if you think about this in classical notation, this would be del u del x plus del v del y plus del w del z. And that is nothing else than the divergence. So this would correspond to gradient of nabla dot velocity vector u. Okay? So the index notation is very useful. It allows us to write relatively lengthy, complex expressions in a very compact format that is easy to calculate with. We don't have to memorize how this differential operator of nabla dot needs to be interpreted. And obviously this can be extended to more complex stuff. So here we have a partial derivative with respect to xj and a second derivative with respect to xk. And what is derived is uj, uk. So what you can find is that there's one index appearing twice. This is the k, here and here. And because it appears twice, we take the sum. So ui and uj are still all the, and here we have the components j. So it's the sum, and we loop through all the j's from 1 to 3, and through all the k's, and take all the possible combinations, and end up with this fairly big guy. And here again, you can see the convenience of the index notation. Now here, we have a quantity that we expect to see in the convective flux term of the Navier-Stokes equations. We have ui, del uj, del xi. So we have one index double. This is the silent index, or in German, stumme index. And we have another index, j, that is not double. This is the so-called free index, or in German, freier index. So this keeps one index. So this must remain a vector. But each element or each component of this vector is a sum. Each component of a vector is a sum over all the values of I. So here we have the first component, second component, and the third component, where the components are given by the j, which is a free index. And here we have the first index for I equals 1, I equals 2, I equals 3, and so on. Okay? So we can use fairly complex expressions, like this guy here, and write them in a very convenient, compact format. Questions now? Okay, so I've mentioned already that the stress tensors are always symmetric. For a symmetric tensor, we have the following rule applying: phi equals phi transposed, and in index notation, phi ij equals phi ji. Now, there's a special convention in this class here for Greek characters. This is introduced because at some points we might actually deal a little bit with chemistry for the turbulent combustion part, only a very brief introduction over one lecture, or actually 10 minutes. But there we are also using some index notation without using the Einstein convention. So the convention will be that if you ever spot an equation that has Greek characters, identical Greek characters, two of them, we do not sum up. Okay, so for this lecture, Einstein convention only relates to Latin characters, but not to Greek characters like alpha or beta. Okay? With that, I'm done with the index notation. If anybody has a question, just feel free to type it into the chat window. I'm monitoring it from time to time, so I can always interrupt and answer your question at a convenient time. So don't feel ashamed or shy of asking questions. Homogeneity and isotropy, they are properties of fields or of tensors, depends. A field quantity is called homogeneous if all values are independent from the location in space. So if we have a tensor field phi ij, and we look at a gradient in any direction xl, and these gradients are 0, then the field is homogeneous, then the tensor field in this case is homogeneous. The tensor itself is isotropic if its elements on the main diagonal have all the same value, and the elements on outside of the main diagonal are all 0. So this here is an isotropic tensor. If you think about pressure, if we have a hydrostatic pressure field or stress field, meaning there are no stresses other than the hydrostatic pressure, then we know we have an isotropic pressure field or stress field. Turbulence itself is called statistically homogeneous if all the statistical mean values are invariant to a shift in space, or actually time, in space. What does this mean? We later on will look at turbulent velocity fields. Just imagine a box filled with turbulence. We have velocities and eddies everywhere. This means we have vortices moving around. But if you look at the mean velocities at all these points, if they are the same, we might have statistical homogeneity. Also, if not just the velocities at all these points are the same, but also the strength of turbulence, then again, we may have statistically homogeneous turbulence. So if the mean values are homogeneous, then we call it statistically homogeneous. It doesn't mean that the instantaneous realization is homogeneous, because then the flow wouldn't be turbulent. Okay? It's a very important distinction. Any more questions about this? Otherwise, we move on. So, how can we analyze turbulent flows? We've said already they are complex, and we have to resort to statistical analysis to study the turbulent flow. Why statistics? Well, we are actually only interested in the statistics. If you look at the turbulent flow, what you are mainly interested in is much of the time the mean velocity. If you look at the drag of an object in a turbulent flow, you are interested in the mean drag. The mean drag averaged over the entire surface, averaged over time. You're not interested in a tiny little vortex that might sit on the left corner of your rear mirror, moving to the right 1 second and moving to the left 1 second, and generating a tiny little perturbation in the drag of your car. If you want to do air acoustics, you might be interested in that. If you want to hear how much noise or predict how much noise your car will make when driving, aerodynamic noise. But for calculating the drag or the lift, this doesn't matter. So what we are usually interested in is actually a mean value in the relevant quantities, because we experience the mean value averaged over all these many, many tiny eddies around you. For engineers, very often the very details of the turbulent velocity fields are not needed. You do not know when you cycle down a hill very, very fast if a little vortex 1 centimeter in front of your left eye is turning to the left or to the right. It doesn't matter. We know anyway that a few moments later it will turn the other direction. This is a property of turbulence. It's random. So we are interested in mean quantities, efficiency of devices, of a heat exchanger or combustor, drag coefficients, and so on. But for the deep understanding of turbulent flows, we may sometimes require to look at the details, but in general, even when we describe things statistically. Because if we describe it statistically, we can do a lot mathematically with pen and paper, with thinking, and the statistics can generate an understanding to us. It's the same thing if you look at the election behavior of the Americans. You are more interested in the outcome of the election than what a certain person in a certain village, in a certain house might vote for tomorrow. This is nothing you are interested in. So let's introduce one concept. Let's introduce a probability density function. This is a distribution function for continuous quantities or a continuous random variable. We take a random variable or statistical variable phi, and we plot this over time. So vertical axis phi, horizontal axis time. If we were in a classical discrete world, you might play lotto, and with lotto you pick certain numbers, different numbers at different points. You end up with a discrete distribution, meaning do not have a smooth curve, but you only have values at certain times. Now in physics, we typically, in particular continuum mechanics, we have to deal with continuous signals. So we might have a velocity at a certain point in the flow field, or we might measure a temperature at a certain point in the flow field. And this might just behave in this kind of random statistical behavior. We don't care about now how it really behaves. We will probably never care about it, but we will care about its statistics. We will care about its mean value, which is illustrated here, the typical standard deviation, which can be estimated as roughly the width of the signal. But we are also, in many cases, and in particular in this class, interested in its distribution. So which signals are very likely? This is illustrated here. If you look at a very high phi value, you will find that such a high phi value is very unlikely and occurs only occasionally, meaning that in the probability distribution for this value phi, this value has only a very small probability. If you are more towards the middle, you will find much more samples, meaning that here we have a much higher probability. So in this case, we have a probability distribution function that looks a little bit like a Gaussian. What is the probability density now? Well, look at such an interval. You might take such an interval and see how many samples we find within this interval. The number of these samples are then the probability to find a value there. If we divide this essentially, or if we consider the width of this, we end up with a probability density. So this is a quick introduction. We are looking into this a little bit further later on. So overall, the probability density function gives the probability of finding a value phi within an infinitesimal interval between phi and delta phi, or phi plus delta phi, in the limits of delta phi approaching 0. So this is illustrated here again. If you compute the total time S, where phi is within the intervals of phi and phi plus delta phi, so where phi is between this line, that line, then we get S. This is the sum of the time spent there. Now, the probability P for finding phi within this interval, so in here, can then be estimated from the sum of the time S, so the total time S within the interval. These are all these time segments. Well, divided by the total length of the signal t. Okay? If we now take t approaching infinity and delta phi, so the width of the interval, then this probability actually becomes the probability density of phi, or the probability density function. P of phi would be S divided by T divided by delta phi for delta phi approaching 0. If delta phi approaches 0, then S will also approach 0, and the limit will be the probability density. Okay, so this was the introduction for the probability density function. You will probably have to think a little bit more about it and look at it, draw a little bit to get a better idea, but I'm happy to take some questions on this. I can continue. The good thing is you can always look this up. I will upload the PDF file later on the Moodle so you can access it. Now we have the probability density function, but we can also look at something else, the cumulative distribution function. So this is given the following way. Here again, on the right-hand side, we see our signal, and you see a quantity uppercase phi. We can now ask the question, how big is the probability of finding a phi value that is lower than our critical threshold value? So what is the probability for finding phi between minus infinity and phi, or in other words, under a certain line, below this line? This is given by the cumulative distribution function CDF, which we refer to as uppercase P. So P is the probability to find a value of phi star that is smaller than phi, where this here is phi star. Find a value of phi star smaller than this phi. The thing about the cumulative distribution function, if you were to calculate the cumulative distribution function for a very large barrier, so you say, how big is the probability that we find phi values or phi star values smaller than this very large phi value, then we all know the probability will approach 1. So the cumulative distribution function grows monotonically from 0 to 1. Let's sketch the cumulative distribution function for this case. Let's introduce here something that's around the lower limit of our signal. Let's call this phi 1. This upper limit would be something like phi 2. Then we can draw the cumulative distribution function over the value of phi, or we have the cumulative distribution function uppercase P of phi. We might have a value of phi 1, which in our case is around the lower limit, and the value of phi 2 is around the higher limit. And we know that we run into a limit of phi equals 1. We start from 0. And the probability of finding something lower than phi 1 in our case is pretty much 0, and higher than phi 2 is also pretty much 0. So the cumulative distribution function would look a bit like this. So something like an error function with pretty much the value of 0 here and the value of 1 here, and in between we have this transition. And now the cool thing is, if you look at this uppercase cumulative distribution function here, and you derive it with respect to phi, so in other words, you calculate the first derivative of this curve here, then you end up with the probability density function lowercase d of phi. The derivative of the cumulative distribution function, the green or pink line, in this case the derivative would look pretty much like a Gaussian, like this. This is our probability density function, and it matches our observation that we have the highest probability for phi's lying in between phi 1 and phi 2. So between phi 1, which is here, and phi 2, so most of the samples that we can find will be somewhere in this region. Okay, so this was the introduction of the cumulative distribution function, CDF, and the probability density function, PDF. These quantities are probably new to most of you. You have to think a little bit about them, but overall the concepts are not very difficult. You can also consider this slide as a slightly more formal definition of the probability density function. Questions? I see a question from Colin Cooper. Which book would you recommend to dig deeper into the probability density function equation? You can look into any statistical book, anything for continuous statistic. It comes very, very early on. It's a relatively basic concept. You just have to get a feeling for what it means. And the best way is actually to think of it as the derivative of the cumulative distribution function. A very good textbook in general will be the book by Steve Pope. Steve Pope, Turbulence. If you Google for it, I think you will only find one book. And there are several copies also in the library. I think we also have it electronically at this university. Okay? Let me see if I can find a link for you. Hold on. Let's see. Here's the man. And hold on. I want to share this link to you too. And here's an Amazon link. I just used Amazon because it's quickest now, but obviously you don't need to buy it, and I recommend to buy it in your local bookstore if they have it. Okay, more questions? The concept reasonably clear to you? Let me just ask, because we have this beautiful polling feature, I can just ask a poll. So, who has the feeling he got an idea what the PDF and CDF are? Hold on. Not yet. Excuse me. Sorry. We have to close this first. This was the old poll. Okay, now we do a new poll. So, who has an idea what CDF and PDF are? Please answer now. Okay, it was a very quick introduction, but I can see that quite some of you are still struggling a bit with it. Can you put it into questions, please? So who has a question? It's important to ask your questions. Okay, guys, I'm sorry, but it's important that you ask questions. But if you plan to just look it up about the CDF and PDF, perhaps also in a Wikipedia article later, that's fine with me, okay? But if you have a question and you ask it now, then I can answer it. This should be helpful. All right, let me just close this poll again. It's closed, right. Good, we move on. What are the properties of the PDF? First of all, a probability density function is always positive. You can have the probability of 0 of finding a certain value, but you cannot have a negative probability of finding a certain value. For infinitely small or large values, PDF approaches 0. So for phi going up to plus or minus infinity, the lowercase p goes towards 0. The integral over the PDF from 0 to 1 is just 1, right? This results from the fact that the PDF is nothing but lowercase p of phi is the first derivative of uppercase p of phi, p phi, where this p here moves from 0 to 1. So essentially, since this guy only goes from 0 to 1, its derivative integrated will be again this p, and hence the integral over the PDF must be 1. Normally the PDF is differentiable. This is not necessarily the case for limited quantities like mass fractions. What does this mean? You might have cases, let me quickly elaborate, where you look at the mixing of fuel and oxidizer in a combustion chamber. Let's say we mark fuel with a value of 1 and mark oxidizer with a value of 0. And now you might have a PDF that is as follows. For phi, we say fuel is 1, oxidizer is 0. And then we might have a situation where we have a lot of pure fuel, a lot of pure oxidizer, and some mixture of these things in between. So we might have a PDF that actually looks like this. This is not differentiables to limit values. Because if you have a quantity that can never be smaller than 0 and never be bigger than 1, then the PDF can become non-differentiable in these locations. One important thing for the PDF, the probability density has the inverse unit of phi. This is important to remember. So the probability density does have a unit. Only the cumulative density, uppercase p, is non-dimensional. But if you derive the non-dimensional quantity p with respect to phi, you end up with a unit, and the unit will be 1 over the unit of phi. One more thing, a very, very important PDF and cumulative density function for us is the Gaussian PDF, and its integral is the error function. Or is a scaled error function. It's not exactly the error function, but a scaled error function. Questions? Comments, suggestions? Yes, Mr. Kuma, waiting for you. Feel free to turn on your microphone and just ask your questions orally. Hello? No, I don't see a question. I don't hear a question. Okay, I'll move on. Let's have a look at statistical moments. Now, the cool thing about the PDF contains that it contains the full information on the statistical distribution of phi. This means it is a function. That means the number of support points it has is infinite. The mean can be calculated from the signal in the classical way you would know it, or from the samples, but you can also calculate it directly from the PDF. So you get the mean value of a quantity phi by taking the PDF and integrating from minus infinity to plus infinity phi times p of phi d phi. So this is the continuous equivalent of calculating a mean value from a discrete distribution function. Same thing happens for the variance, or the square of the standard deviation, because this can be computed as phi equals phi minus phi prime square barred. This is the variance. It's the mean value of the square of the fluctuation or deviation from the mean value. And this can be calculated the following way. So consider this also as a definition for the variance. It's the integral from minus infinity to plus infinity of phi minus the mean value of phi to the square times the probability of phi d phi. And we can also compute higher moments, third moments, fourth moments, and so on, is given in this expression here. So you see what changes for the nth moment is that we just have to add an index or a power n here. Now, if we look at a PDF, again, let me draw or sketch a PDF. So this is P of phi. This here is phi, where the units would be, it has the units of phi, and this has the units of 1 over phi. Let's assume we have such a PDF here. Then it's clear that the PDF itself is a continuous function. It has an infinite number of points, whereas the moments that we can calculate, well, if we have calculated 3 moments, then we only have 3 values. Meaning that the PDF itself, which has an infinite number of values, can let us calculate an infinite number of moments. Now it turns out that this infinite number of moments is theoretically sufficient to calculate the PDF again. This means the PDF is determined if all its moments are known. But in fact, it's generally quite well approximated by its lowest moments. This is a very important property. So such a PDF here, as the blue one, that looks, the lilac one that I've just drawn, that looks almost like a Gaussian, can be approximated, for example, very nicely by assuming a Gaussian function of this mean value here, and perhaps the standard deviation. So if I draw this Gaussian, we look a lot similar already. If I want to approximate it better, I can also use a third moment, a skewness, so a little bit of an asymmetry, and use a different shape function, not a Gaussian, but something else of a bit higher order. Then we can already get a fairly good fit of this. So where the PDF is determined by all of its moments from order 0 to infinity, it's usually enough to approximate it by its lowest moments, at least if the PDF is smooth. Okay, I have a question here by Mr. Kumar. Mr. Kumar, one thing when you log on, you should log on with not just listen in, but also using your microphone. There's a log on option. You can mute your microphone as soon as you are logged on, but if you log on without considering your microphone, you can never turn it on again, okay? And I think this applies to most people attending this lecture, because if I look into this little chat bar on the left-hand side, I see a few people with microphones muted, about 3 or 4, and everybody else seems to have a headphone symbol. With a headphone symbol, you can't turn your microphone on. So please log on such that you can turn on your microphone later on, but mute it. Okay, yeah, thanks, Mr. Kumar. This was just a comment, so nothing else to add from my side. Thank you. Now we can look at joint probability density functions. This is going to be a bit more fun, and this is some of the difficulty we typically have with turbulence. Turbulence does involve several random variables that can depend on each other, starting with the different velocity components u, v, and w. Are they independent or related? How can we find out? What can we say about the relationship between these variables? Now let's look at a certain thing. Here we look at the probability density for phi I, phi 1, and phi 2. For the interval width, we look at the probability of finding the values phi 1 and phi 2 for intervals of the width delta phi 1 and delta phi 2. And that yields the probability that phi 1 belongs to the interval of phi 1 to phi 1 plus delta phi 1, and for phi 2 to belong to the interval phi 2 plus delta phi 2. So what does this mean? Here we have a quantity phi 1, quantity phi 2. Here we choose a certain phi 1 of interest. We choose here a phi 2 of interest, and we have an interval of height delta phi 2 and an interval of width delta phi 1. And then P, this probability here, is the probability of finding points or samples within this zone, right? So that way, we have the probabilities there. If we now do the limit of delta phi approaching 0, we can make this zone smaller and smaller until we reach just a point. And this would then again be our probability density function at this point. For the joint probability function, the following properties apply. First of all, the integral over the joint probability density function must be 1. So if we integrate phi 1 from minus infinity to plus infinity, and phi 2 from minus infinity to plus infinity, the integral of the probability density phi 1, phi 2, del phi 1, d phi 1, d phi 2 must be 1. Yeah? So again, this general property of all probability density functions is the integral over the entire variable space must be 1. And obviously again, the probability density of any phi 1, phi 2, so of any point, must be greater or equal to 1. Now the question is, if we want to have the PDF for a certain value phi 2, the let's say we want to see the PDF along this line, the one-dimensional PDF, not the joint probability density, but the one-dimensional. We can do it calculating it this way. So the probability density function of phi 2 is the integral from minus infinity to plus infinity of the probability phi 1, phi 2, d phi 1. And similarly, we can do the same thing for phi 1. Okay? So bear in mind, we are not going to do PDF methods later on. That means the probability density functions are nothing that we are going to deal with in too much detail, but you should be aware of these concepts. You should be aware of the joint probability density function. First two moments of phi 1 and phi 2 can be calculated the following way. We can calculate a mean value, and now we need a double integral over phi 1 and phi 2. And this is how we get the mean value of phi 1. Take phi 1 and multiply it with a PDF, d phi 1, d phi 2. And for the variance, we can also calculate this. So the variance in the quantity phi 1 is obviously calculated from this expression and can be determined this way. So you have some calculation rules for PDFs. We are not using them a lot later on, but I'm showing them to you so that you get an idea of what these PDFs and joint PDFs actually are. Now we move on with the joint probability density function. We can have something quite interesting, and these are joint moments. So we can look at a quantity like this, phi 1 prime, phi 2 prime. This would be something similar to a variance, but it would not be a variance, but it would be a so-called covariance, because it's not the variance of phi 1 with phi 1, but it's the variance of phi 1 with phi 2. So between two different quantities. We would calculate it from phi 1 minus its mean value, phi 2 minus its mean value. So this here is deviation from the phi mean, phi 1 mean. This is deviation from the phi 2 mean. And the probability density gives us this quantity. And this quantity is the covariance of the two quantities phi 1 and phi 2. It's also referred to as the mixed second moment. And this is related to the correlation. Look at this quantity. This quantity will be very large if phi 1 and phi 2 are large at the same time or small at the same time. But if one of them is large and the other one is small, or the other way around, this quantity will take negative values. So this is a measure for discussing how two quantities are correlated. And about this, you may want to read a Wikipedia article or look a little bit more into a mathematical textbook, although we are looking at more examples of this later. Statistical independence occurs if we can write that the probability for the values phi 1 and phi 2 can be calculated as the product of the probability for phi 1 and phi 2. And if these quantities are statistically independent, then they are also uncorrelated. What correlation is something we are looking at later. Now here we have some joint probability functions, and from the joint probability function and the covariance, we can calculate a correlation coefficient. So here, with the covariance, and down here, we just have an expression of the variances. So this is the variance of phi 1, this is the variance of phi 2. We take the product of these variances and the square root over it. So this is a normalization, meaning that the correlation coefficient will be within the range from -1 to +1. And the cool thing is, it shows us how these two quantities depend on each other. So if you have one random value, phi 1, and one phi 2, and we find samples where when phi 1 is large, phi 2 is also large, or where phi 1 is small, phi 2 is also small, and this is always the case, and we get points and samples along this line, then we would consider it as perfectly correlated. The correlation coefficient would be 1. In this case, these points are spread out a bit wider. We would end up with something like a lower correlation coefficient. In this case here, There's no real correlation apparent. You would not say we can fit this with a line or model the distribution with a line. It's just nicely spaced out. Here, however, we see that now if you wanted to fit this, such a line dropping down with a little bit of spreading left would not be a bad fit. So now we have a negative correlation coefficient, meaning that if we find high phi 1, we are in this zone here, where we only find low phi 2. And the other way around, for low phi 1, we find high phi 2. So this is negatively correlated now, and the correlation coefficient will take a negative value somewhere between 0 and 1. Here in this case, we are almost perfectly negatively correlated, so we can say that if we find a positive phi 1, we'll also find a negative phi 2. Now, be very aware. This is a typical discussion. It's very, very commonly discussed in the medical field, correlations and causations. First of all, the big rule is correlation does not imply causation. What does this mean? If you find that, for example, more children are born in summer than in winter, and you find that in summer it's hotter than in winter, then you know that just by increasing the temperature in your house will not increase the number of kids born, even though you can increase the temperature. So the high temperature is not the cause for the number of kids born. The cause is a different one. The reason for the many kids born in summer is not the high temperature. So these things are correlated because you have many kids born in summer and it's hot in summer, but there's no causal connection. So you cannot explain one with the other. In the past, this was a big problem with medicine because very, very often doctors were A, very bad with statistics, and B, didn't understand this. So doctors would have some really crazy therapies. They would use, for example, mercury or quicksilver injections, hoping to heal the patients with that. And many of their patients got healthy again. So they found they give mercury, which is very toxic and very bad for you, to the patient, and the patient gets healthy again. So the doctor believes mercury and getting well again are correlated. No, they are not. The patient would have just improved without the mercury as well, but the doctor wanted to believe that this was his mercury. And this brings us to the next problem, because the doctor did not see just the correlation that he could observe, which is patient is ill, give him mercury, and he gets better again. But he also thought that there was a causation, so he thought that the patient got better because of his mercury. But obviously, this doctor did not do independent tests without giving mercury and checking what is more successful. So this is very important to understand that these two things do not depend. And here's an example. Sleeping with one shoes on is strongly correlated with waking up with a headache. Obviously, if you go out boozing, you come back, are so sick and feel very bad, you fall on your bed, and the next morning you wake up with a headache, and you find your shoes are still on. Don't believe that wearing your shoes causes the headache. And when you are a child and you read a lot of books at your junior life, and you fall asleep late with the light on, you are likely to develop myopia, Kurzsichtigkeit auf Deutsch. But this myopia is not due to the fact that you sleep with a light on, but it's due to the fact that you might have read a lot from a book without wearing your glasses, holding the book very close to your eyes, or doing something else in it. So there's not a causation between sleeping with the light on and myopia. And here's another example as a plot. Somebody found these beautiful correlations that are not linked to any causation. Here is US statistics per capita consumption of cheese. So how much cheese do typical Americans eat per year in pounds? And you also see the unfortunate number of deaths of people who died by being tangled in their bed sheets. So by getting lost on their bed and not being able to breathe. Actually a very sad quantity. But if you look at this, you find it's almost perfectly correlated. And you might be tempted to assume that there's a physical connection. And you might assume that the amount of cheese people eat causes these deaths by tangling in the bed sheets. Obviously, this is wrong. So this is very important. You always must remember that correlation does not imply causation. Why do I tell you this? I tell you this also so that you understand better what correlation is. Right. Let's have a quick break for 1 or 2 minutes. I will also be happy to take some questions, and then in 1 or 2 minutes we can continue. Any questions? Good. Let's move on. Let's look at 2-point correlations. In general, when we study turbulent flows, it's important to understand the statistical, spatial, and temporal information. And we need to see how information is linked between 2 points. So if you look at a flow field, you might ask a question, if I know the flow and the velocity at 1 point, can I also determine the velocity 5 centimeters away for it? This means we need to find statistics between 2 points, 2-point statistics. And we can describe the interactions of points in a field with a given other point mathematically by so-called 2-point correlations. So this here can be calculated as the velocity fluctuation ui prime at a point x and at a point x plus delta t, and this gives us the correlation. This is the autocovariance, and for the distance between the points in space and in time approaching 0, we get to the limit that is given here. We have a tensor notation for that. We are not doing too much with these 2-point correlations, but I just want to show you a few interesting properties because they lead to some length scales. We can skip this here. We skip this here. But I want to show you this. So here, the vertical thing is the longitudinal 2-point correlation. About its definition, you can take the slides going a little bit back. What it describes you is how in a flow field like this here on the right-hand side, where we have a jet emerging from the bottom, going upwards, and you see the colors showing the velocity. So red is a very high velocity, blue is a low velocity. So here, we have a turbulent flow in a simulation with very high velocities pointing upwards. And now we might just look at 2 different points, separated in vertical direction, separated in direction delta x. Point 1, point 2. Now the question is, are the velocities there connected? Well, we expect that if you have 1 point here and a second point downstream from it, there's a connection, because if you have a high velocity here, it's quite likely that we have a high velocity here too. If the spacing of the points is bigger, so we compare this point with that point, then the connection is less strong. And it's less likely that we see a strong correlation. And this is represented here by this plot. This shows us the longitudinal 2-point correlation. The horizontal axis is the distance between the points. We observe a correlation function that looks like this. Obviously, when the distance is 0, the velocities at these points are perfectly correlated because they are at the same point and hence the same velocity. If the spacing gets bigger, the correlation drops towards 0. So if you just find a very fast lump of flow with a very high instantaneous velocity in this region, it's clear that a point that is very close to our original point will show a nice correlation. But a point that is outside this region of this fast flow will not be correlated. This is illustrated here. We get the high correlation for points close by, a low correlation for points far apart. We can not only look at the correlation of the velocities in axial direction, spaced out by points, spaced out in axial direction, but we can also space out the points in spanwise direction or sideways direction. So here, this, and we end up with this correlation function, and this time plotted not over the axial spacing of the points, but plotted over the sideways spacing of the points, so delta y. The interesting thing is, now we observe a similar thing. We see that for no spacing, the correlation will be 1, but if we get to a certain spacing, the correlation will be 0, and the correlation will actually be negative. Meaning, for this type of distance, that if we find a high velocity pointing up here, high velocity fluctuation, we are likely to find a negative velocity fluctuation on the other side. Or if we find a positive fluctuation here, we are likely to find a negative fluctuation here. Now, how can that be? Well, this is interesting because what it implies is that we may actually find turbulent eddies of this size looking like this, or in the other direction, looking like this. So if we have eddies that are typically of this size, or let's say of this range of sizes, then we can expect such a negative correlation for this lateral two-point correlation. So this way, we can, by looking at the correlation functions, get an idea of how big the eddies are. And this is quite useful. It gives us some idea about turbulence. Before I move on, any questions so far? We are not looking in detail at the correlation functions, but we want to use them as a tool to see how turbulence can behave. So we just had this very brief introduction. I think like most of the stuff that I've been showing to you, you have seen it in the mathematics classes already. You might have seen some stuff in the fluid mechanics classes and so on. This is meant as an introduction, but also as an opportunity for you to look into some of these quantities again if you feel you need to. Right, then let's have a few words on dimensional analysis. Who of you has done something with dimensional analysis or knows what dimensional analysis is? So if you have done some dimensional analysis oder dimensionsloses Arbeiten, Buckingham P und so weiter, please tell me. So, yeah, yes, you've done something with that. Okay. So what is this about? You might have wondered yourself why all our physical equations are so beautiful. Why do all these physical equations fit so nicely? Why are there rarely any correction factors in the equations? Why can you just calculate power from force and distance without having a model constant? Why can you just differentiate one quantity to get another nice quantity from physics without having to add some factors and so on? And it turns out that our unit system is based on very, very few quantities and everything else is derived in a way that we do not need any tuning constants. But it also turns out that any meaningful relation in physics must hold independently of units. It's clear that if you want to have enough water per day, you need the same amount of water when you are in the US or in Germany. But in the US, you would go to a place and buy a certain amount of gallons of water, and here you would buy it in liters. But overall, the real physics and what it's all about doesn't care about the units. You can do the same thing in gallons, pints, or liters, as you can do in other quantities. Now, when you look at a physical relationship, a meaningful physical relationship, it turns out that it must be homogeneous in its dimensions, meaning it only makes mathematical and physical sense if you have the same dimensions, the same units on both sides of the equations. Now, this is cool because it means that you can also derive equations for something that you don't know. You can just look at the units and can play around and look what equations are actually possible based on the units. And this can be done very nicely and formalized using the Buckingham Pi theorem. You can have a look at the Buckingham Pi theorem to find out how to find meaningful dimensionless parameters that describe the physics, and that can be used as a basis for nice mathematical relations describing the physics. So this is cool because probably most of the time you have never looked at the units only to check if your equation might be correct, but actually you can use the equations, the units, as a requirement for deriving equations. And this is what was done with dimensional analysis. And in turbulence, where very often we don't understand the physical connection between two statistical quantities, we'll often make use of this. So you may want to look at dimensional analysis, Dimensionsanalyse, or the Buckingham Pi theorem, just to get a better idea of it. It's actually fairly cool if you've never done it. Now we are coming to the end of the lecture, just some very general revision of balance laws. This is essentially the same stuff we do in fluid mechanics too, so most of you will have seen it. The fluid motion is described by the balance laws for mass, momentum, energy, and if you go to combustion or chemically reacting flows, chemical species. So in general, with an accumulation term, it's the partial differential with respect to time. We have the convection term. It's a partial differential with respect to space, which describes as the convective fluxes. So how a quantity is transported by convection, by advection, so by motion with the fluid. Here, we have the diffusion term. And then we are left with a source term for any other things that will be left. So the conservation of mass is written by this equation here. It's given here. We have an accumulation term of mass. The change of density in a point results from the convection term. So it results from the density that is pushed to this point by the flow at velocity u. The density is constant. We can simplify it to essentially say the divergence of the velocity is naught. For momentum, we can write a similar equation for accumulation. So the change of momentum at a point results from the convection. So how much momentum is shifted to this point? Viscous forces, or for constant density, it's actually just diffusion. Gradient of pressure, because the momentum at a point will be changed and increased if we have a higher pressure on one side than on the other side. And here a gravitational term. And if we apply constant density and viscosity, we get the simplified form. Here again in index notation, so ui actually corresponds to the vector u. We have to write this equation for all three I components, 1, 2, and 3. And to remind you, we don't have to write it for all j components because we just sum up overall the j components from 1 to 2 to 3. And that's it for this lecture. So this was a little bit of mathematical background, a little bit of revisions of what you might have seen and done before. Any questions? I'm happy to take some questions. I'm also happy to take suggestions, comments, or recommendations. Please shoot ahead. Comments, questions, suggestions, please type them into the chat window or open your mic and talk to me. All right, there's not very much. So bear in mind, these are some concepts that I wanted to show to you to get an idea of what's going on. calculation, definition of mean and variances are very important. You absolutely need this. The transport equations are very important. You need them. Index notation is very important. You need that. The correlation functions, the correlation index, the two-point correlations, they are slightly less important. But you see, throughout the lecture, we are going to work with these things from time to time in a way that it will become more and more clear what it is. So these slides that I've presented to you here should also be very useful for your preparation for the exams. Now I see, yes, Mr. Cooper, you have a suggestion. Please go ahead. First, my suggestion to everybody, make sure that with your phone, your computer, whatever device you use, you log on such that you can turn on the microphone later. Yes, Mr. Cooper. Some sort of simulation for better understanding. What do you mean by some sort of simulation? Everybody, I assume your computers always have a camera and a microphone, so please log on such that you can participate in the discussion next time and can turn on your microphone. Okay, yeah. Yeah, Mr. Cooper. Look, I'm just doing this little introduction here. It's a summary of some stuff that you will have mainly been taught already in other classes. I mean, much of this should be more or less familiar from school, from mathematics courses at university, from fluid mechanics lectures, and so on. So I just want to give you a quick summary, a quick reminder. You should look through these slides again later on. Think about them. If you feel that you are going to understand these things, just continue the lecture and remember that you can always look up these things. If you have time, look them up now and try to understand them better, okay? But yeah, this was just an introduction, just providing some foundations, just providing some stuff that we may be looking at again later on. Okay? Good. Then I'd like to thank you, and I think Luis Cifuentes is taking over now. Yes. Thanks, everybody. Have a good day. Yeah, thanks, Luis.
Okay.
Bye.
You're welcome. Okay, everybody. We will continue with the tutorial section. But let's take a break, maybe for 8 or 10 minutes. Relax. Yeah, let's take a break of 10 minutes. We'll come back at 10:30. Yeah. Okay. Hmm. Can you hear me properly? Just type yes in the chat. Okay, thanks. Yeah. Okay, this first section is very basic. We are going just to review the notation index, subqueries, and the basic vectors. Unit basic vectors, i.e. This index notation, which is very useful for scalar products, typical axis label S, Y, and Z in other bases. So, before starting with this first exercise, let's review how we can check a vector with this notation. A vector can be represented. With this notation, which is very well known. Second, let's say vector A, but using the basis vectors E1, E2, and E3, this vector can be represented in this manner. Which is in this notation, it's very compact. This vector takes the form like this. That means that we have a summation, we have a summation in index. So, when we have this summation, the scalar product in index notation, let's say that we have vector A dot vector B. This scalar product can be represented with this index notation in the following manner. In this manner. Or using another index, J, like this. It means that what we have is just this summation in index notation. Let's say from 1 to 3. Or using the basic vectors, this scalar product can be represented by the following notation like this. Dot in this manner, let's just come back to this notation, and say that we have this vector here, A, and this vector B here, and we're going to get the scalar product of this vector represented by A this B vector. Yeah. The scalar product between these two vectors is J and this alternative manner dot between the bases. Just use J and the coronator. Just yeah. And as Professor Andreas mentioned this morning, when we have this product here, it means that we have a summation using the same index. In this case, A1, B1, A2, B2, A3, B3. This is how we reproduce or represent this scalar product between vectors. At the end, it's represented in this manner, and it's just a summation for every index using both vectors. The index notation is very useful, and it's also commonly known as subscript notation, and is an extremely useful tool for performing vector algebra. Now, for example, let's plot this. Consider the coordinate system the following manner. I'm just gonna do my best. Say that we have this vector here. We have the basic vectors. E1, E2, and this is normal coordinate S1, S2, S3, and we have here E3. And we have this vector named A. This vector A can be decomposed in three components. Let's say have this. And we have the first component in this direction. So this is A1 modulus. In the first component, in the first direction, we have A2 here. And then let's say that we have here third component here, A3. Instead of using the typical axis labeled Y, X, Y, and Z, we use, in this case, we use X1, X2, 3, or this coordinate system here could be represented in this index notation xi with I varying between 1, 2, and 3. The corresponding unit basic vectors are, in this case, E1, E2, and E3, or in index notation, it's just this one, where the E varies between 1, 2, and 3. The basis vector E1, 2, 3 have the following properties. Let's see if I have space here. Yeah, E1 dot E1 is equal dot E2, E3 dot E3 equal 1. Or when we permute the index, let's say E1, E2, equal E1, E3, E2, E3. In this case, we have the case equals 0. We already show here the Kronecker delta here. And this is very useful for this index notation. And this delta, Kronecker delta, has the following properties. Please, just 1 second. Is 0 when we have different index. Let's say when I is not equal to j, and is 1 when they are the same. They are equal. And these two index varies between, let's say, E and J from 1, 2, and 3. And this delta, this Kronecker delta symbol comes from the scalar product between these basic vectors. So it means that what we have is the Kronecker delta is just this mathematical operation what we have here. Another important symbol is just the Levis beta symbol with 27 components. This is just a review, very quick review for solving the exercises for today. The Levis beta symbol, let's make here. It's just represented by E, J, K equal 1. Just if the index I, J, K so this, if I, J, K is an even permutation. So or cyclic permutation, yeah. Of 1 to 3. I mean, when we have E to 3 equal to 3, 1, or E 3, 1, 2, this is equal 1. Equal 1. 3, 1, 2 is equal 1. Another case is for the Levi-Civita symbol is -1, but in this case it's -1 if this ijk, let's say here, it's a not permutation, non-cyclic permutation. So it means that when we have these options, 3, -1. Oops. Okay. 3, 2 is equal -1. And 0, the case with 0, is just if 2 or more subscripts are the same. So 0, we have just E112 or E313. This is equal 0, etc. No, and on other cases. A very important identity involving the product of two permutation symbols is the following. Say that we have this Levi-Civita symbol, product with another tensor. It means that we can represent this product of two permutation symbols using the delta, Kronecker delta. Like this. First with I, and then I continue with the J. M, J, N, J, N, and then with K. Oops. And we solve this matrix here. But what about if we repeat one index? Let's say if we have the following. J, another permutation, but in here we will repeat the index. Okay. Okay. Show the matrix. The J. J. And here we have a double index here, which is this one. As we know, in this case, the repeated index k implies a summation over all values of k. So what we have here, okay, oh my God. Okay, let's drop again. This platform is a little bit complicated. We have again delta IL delta K 1K delta JL delta AN delta JK delta KR delta KM, and here we have delta KK, but in this case the repeated index is just a summation over all values of K, so it's just 3. Yeah. Let's solve this matrix very quick here. So what we have here, just there, this guy with this guy, here, AM, now minus 3 AL minus delta KL delta JK, and now plus this first guy here, K delta JR delta KN KL delta JN. So solving this, you will end up with the following expression. This one, delta IL AM IL delta JN minus delta IN JN. So it means that when you have permutation, this product of two permutation symbols with the same index, you have always the following expression omitting this index here for this equation. Yeah. So you use the first index here, combine it with LM, and then the second one, J, yeah, for this guy, combine it with LM here, M and L here, yeah. It's very important for the coming exercises. Another expression for permutation symbols, yeah, and just if you are writing down this question, just take your time. I'm just checking the chat. Yeah, it's very useful if you write here in the chat if you have some question, or maybe just try to activate your microphone if you have any question. Interrupt me at any time as you like. To now, if you don't have comment or question, I will continue. that we can represent these two permutation symbols, the product of these two permutation symbols, in the following manner. Changing the index, say that we have this guy here. And PQ, another index, we repeat the index I. Oops. Q. JQ. AP. This is AQ. P. KQ minus JQ with the KP here. Double dot product between tensors. So between tensors. It's represented with these symbols. Let's say with bold. In bold, normally in bold and capital letter. Tensor to index IJ and VIJ in notation index. It means that this is just summation between every index. So what we have here is just A11 and V11 plus changing the index for J, A12, B12 plus A13, B13 plus A21, B21 A22, B22 A23, B23 plus A31, B31 plus A32, B3, B32 plus A32, B33. Another thing that you should know is just the cross product between vectors and how we represent this cross product with the notation index. Okay. Over here. AI with the basic vector like this, cross bj basic vector j, and this is just AI bj AI cross basic vector AI in j, and this is just equal to, with the Levis beta symbol represented in the following manner. It means that we have another vector from this cross product. The vector K. Yeah. This one. Very simple and very well known. This cross product is just using this matrix here. Oops. Yeah, this is just a review for using this color product notation index that we will use for solving the exercises. This one. So if you have a question to now, just let me know. If it's not the case, I will continue with the first exercise. Okay. I don't see anything in the chat. Okay, let's move on to the first exercise. Exercise 1.1. Say, write this equation in long terms for the index going from 1 to 3. So we will use the index notation that we already reviewed. So for the first exercise, you have this exercise on Moodle, so you can download it and follow the. Yeah, you can download it and download the Mr. Sada. Yeah, you can download this exercise on Moodle. But let's zoom in. Yeah, we're going to solve this guy for the index going from 1 to 3 in long term. This is the first one. And I will continue with this one, etc. Okay. So we have this vector. Okay. Exercise A. I don't want to say A, just directly with the exercise. Ci equal Ij plus the Kronecker delta symbol Ij Bj. So this is direct. We see here that this is just a vector Ci, and just we have to vary the index from 1 to 3. So for the first index C1, and the rest is just summation varying the index J. So what we have is just A 1 1 plus 1 1, but when we have the same index in the Kronecker delta symbol, we have a scalar which is just 1 and B1 plus the rest, when they are not the same index, we have 0 for this Kronecker delta symbol. So other options that we have is just A2, B2, and plus A1, 3, B3. Solving for the second part of this vector, C2, is just A2, 1, B1, because in the using this Kronecker delta, 2, 1 here is 0. So A2, 2, Kronecker delta 2, 2 is just 1. 2 plus 2, 3, 2, 4. Last component is just A 3, 1, B1 plus A 3, 2, B2 plus A 3, 3. In this case, is the Kronecker delta 3, 3, so 1 and B3. This is the equation in long terms using the index notation. Okay, this is exercise A. Let's move on to the exercise B. We have this scalar, because we don't have any index here. We assume that that is a scalar, so every symbol that we write down on the right hand side is just a summation. So what we have is just A, M, M, AM, N, plus B. Yeah, this one. Okay, so we have here directly N1, N1, N1. New N1. N11 and with the N12 plus just replacing the index value for varying the AM. A2, A2, A21, A1 plus A2, A22, A2, and then A2, A23, A3, and then A3, A3, A31 with A1 plus A3, A3, 2, and A2 plus A3 with A3, 3, A3, and then for BK just to square, summation, B1, yeah, to square, plus B2 to square, plus B3 to square. To square. Very long term for this scalar. Yeah. Okay. Just gonna give you 5 or 10 seconds to write down this very long equation to continue with exercise C. All right, let's move on. Okay, we have here the C. C is just this one, this identity, just CIK minus lambda Kronecker delta IK VK equals 0. Okay. What we have here is a vector because here in this case we have this replacing the index value for every index. We have C1, 1, yeah, minus lambda when k is equal 1. Summation, this is just 1 and 1. That's why we have the value of lambda here. Plus C12, B2, plus C13, V3. Yeah, the first component is 0. Varying I, second index, here 2, 1, 2, 1 for the Kronecker delta is 0, yeah. That's why we have here this just, oh, sorry, yeah. Yeah, C21, V1, plus, okay, C22 minus lambda, yeah. In this case, we have delta, Kronecker delta 2, but it's just 1. That's why I just want to write down here lambda. B2 plus C23 B3 equals 0. And then continue with the third component, the C3. 1, 3, 1 for the Kronecker delta is 0. That's why I just use this. V1 plus C3, 2. Kronecker delta 2 is 0. Okay, V2 plus C3, 3. Now we have 1 minus lambda B3 equals 0. Yeah. This is the solution for exercise C. D. Yeah. Have sigma yj. In this case, this is a tensor with 9 components. ij. So we have sigma 1, 1, sigma 2, 2, sigma 1, 1, sigma 1, 2, sigma 1, 3, etc. 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3. And this sigma is represented with the following expression: lambda, k, delta k, e k k, plus 2 ij. So for the first component of this tensor with 9 components, say that we have here sigma 1, 1. Okay. And this is just 1, 1 summation. So we have lambda summation for this basic tensor A11 plus A22 plus A33 plus 2 no E11, which means that we have the following: lambda plus 2 nu E11 plus lambda E22 plus lambda E33. So sigma 22, I'm just going to do the same. Lambda 1, 1 plus 2, 2, 2, 2 plus E33. Those no E22. This is equal lambda E11 and plus here plus lambda 2 no E22 plus lambda E33. Let's do the same for sigma 3, 3. So for the diagonal of this tensor, 1 E22 3, 3. No. This is 2 3, 3. And this is okay with this. So we have E11 plus lambda, let's say E22 plus here lambda plus 2 no, oh my god, E3 no, okay, this is E33 3, 3. Continuing with the non-diagonal components, okay, we have second. Sorry. Sigma 1, 2. 2 nu 2. Yeah, sigma 2, 1. It's just 2. 2, 1. It's just 2. No. E 2, 1. Sigma 1, 3. E 1, 3. Sigma, what is the other? 3, 1. 2, E 3, 1. The other component 2, 3. Sigma 2, 3. Sigma, 3, 2 is the last one. 2, E 3, 2. So we have for the diagonal, we have these 3 solutions. Sigma 1, 1, sigma 2, 2, sigma 3, 3. And for the non-diagonals, this the other components or these ones. Okay. Let's move on quick here. Yeah, the last exercise is very easy. It's just E. It's just this scalar equal alpha Kronecker delta Ig, and this is just summation in the diagonal of this Kronecker delta, which is 1, 1, 2, 2, 3, 3, which is just 3 alpha. That's it. Okay, exercise 1.2. We have here exercise 1.2, calculate the numerical value. Let's say if we have here one, calculate the numerical value of the quantity phi with this expression. Okay. So we have the following expression. Phi equal 5 delta Ij delta Jk delta Ki plus Ijk Ipq Ij Ik, a lot of indexes, P and AQ. Okay. And then what we see here is that this index is a repeat index. So let's show to you slide number 1 second. I cannot move that. And according to what we show here, using this product here, we can represent this double product of these two permutation symbol in the following manner. So So we have the following: 5, 5, or omitting this J and J here is delta IK delta IK delta KI plus 2 delta KP and delta KP, because we have repeated this index here for these two permutation symbols, minus delta KQ times delta KP P and for the moment just going not going to touch this AQ. Okay, and then reducing the index, let's say this KK here, so we have delta II plus 2, and now I'm going to multiply these guys here, A, J, A, K, A, J, yeah, and A, K here, minus AJ, AK, AJ, AK. They have the same index, so we cancel. We will end up with this delta Kronecker with repeated index. So at the end, what we have is just 5 and 1 2 plus delta 3 3 3. The diagonal of this Kronecker delta, so this is 5 times 3, this is just 15, yeah. All right. Okay, I want to give you 5 or 10 seconds for question or comment about it. If this is not the case, I will continue with the exercise 1.3. Okay, I don't see any comment in the chat. Okay. Yeah, exercise number 3. We have these two vectors, A and B. Yeah, 1 second. We have this vector A and B. Yeah. And we have to calculate this operation. This is just a scalar. There is no index for this symbol here, so it's just a scalar. So let's do this. Yeah. We have for this exercise that the vector A 1 second. It's represented in the following manner. Yeah, this platform. Okay, here A is equal to A1 as 4, 2 minus A 3, and B is 3B1 minus 7E2 plus 3E3. And we have the following expression here. I'm just gonna try. Which is this one? AA, AI, BI, AJ, BJ minus AI, AI, BJ, BJ. AM, AM. Yeah. Okay. First of all, these two guys here are the same. This guy here and this guy here. This is just AI, VI is equal to A, J, VJ. Taking into account these vectors here, what we have is just 2 times 3 minus 4 times 7 minus 8 times 3, yeah? Yeah. And this is minus 46. On the other hand, these guys, this guy here and this guy here are the same. Yeah? So, I is equal AM, oops, what I am, AM, yeah, 2 times 2, yes, 2 square, but it's basically that. Anyway, we'll continue with this notation. Plus A, which is 84. And the same for this guy here, yeah. BJ is just 2 square, yeah, so at the end, this is just 3 times 3 plus 7, so we will end up with 67. So this expression here, yeah, just replacing the values. Easy peasy. Yeah. I'm just going to give you 10 seconds for some comments or questions. For exercise number 4, we have a matrix. Okay, I don't see any comments in the chat or questions. So, for this exercise, we have this matrix here. And we have to calculate these 4 operations. They are quite simple. Okay. The first one. Just gonna write down here the matrix. Matrix A. It's just this guy here. 2 minus 3 minus 1. 7. 4. 5. Minus 5. 3 and 1. Okay. First exercise is just to get this APP. As you know, it's just the diagonal. Yeah. And this one here. So this is just A11 plus A22 plus A33. So this is just 7. Yeah. Then B is just the product of this matrix with the following index: A, P, Q, A, P, Q. Yeah. So in this case, we have a scalar. We'll start with the index 11, A11 times A11, and then I will vary the index Q plus, okay, index Q is 2 here, and then A12, and then Q, A1, yes, 3, A13, and then plus the rest, 21, A21 plus A22, A22 plus A23, A23 plus A3, in this case 3, 1, yes, and A31 plus A32, in this case, wait a second, 32 plus A33 and A33. So this is just the square. Every component, this is just 3. So, let's write down here. This is just the square of every component, as you notice. And so weiter. A2 to square plus A2 to square plus A2 3 square, 2, 2, 3, yeah, okay. 3, 1 to square, and etc. 3, 2 to square. 8, 3, 3 to square, replacing the values. We have that this is, 139. Okay. Okay, I'm just going to give you 5 seconds for any comment about it. No. Okay, C. Yeah, if you checking the exercise number C, C is this one. Yeah, APP times, what a P, APP times AQQ. Yeah, but we already have this PP here, no? So, for exercise C, which is A, P, P, A, Q, Q, we have the, oh my God, okay. Wait a minute. A11 plus A22 plus A33. That times the same. A11 plus A22 plus A33. Yeah, this is just a square. Replacing the values, this is just 49. For part D, we have a Levi-Civita symbol. It's this one. E, P, Q, R. A, P1. A, Q2. A, R3. Playing with this, with the permutation of this Levi-Civita symbol, we have the following. Yeah, A1, 2, 3, A1, 1, A2, 2, and 83. 3 plus, yet again, A1, 2, no, in this case, A2, 1, in the other way around, A1, 1, A3, 2, A2, 3, and then A2, 3, 1, A2, 1, A3, 2, A1, 3. And then the other component 2, 1, 3, A2, 1, A1, 2, A3, 3, plus A3, 821, 831 in this case, 822, 813, and the last one, 122, yeah, 831, 831, 812, 823. And then what we know is that, and in this Levi-Civita symbol, ijk is equal 1 if these symbols, these index are even permutation, minus 1 when they have an odd permutation, or 0 if we have subcrease with the same index. So I'm just going to switch here very quick. Also, let's continue here. One, 822, 833, 811, 832, 823, plus 821, 832, 813. In this case, minus 21, 812, 833, minus 831, 822, 813, plus 831, 812, 823. And then replacing the value for every component, we will end up with this scalar one. I just go back here for those people that didn't have time to write down the full equation. I will give you 10 seconds to continue. Okay. And this one. Yeah. I see some comments here. Man Chang. Where? First 3, 3, 1. Yeah, we have the Levi-Civita symbol E321. E321 is negative. That's why we have minus 831. Yeah. A321 is negative. The last exercise is 1.5. It's quite easy. This is just, we have to write the following equation in index notation, so it's not that much. Let's check the exercise. If I have the exercise here, 1 second, let me show it to you. Yeah, this one. So very easy. We have to write down the exercise in index notation. So quite easy. Let's do that here. Then we have the first one, this one. This is just the following, yeah? This is just a vector. As you know, we can represent this vector in the following manner, like this. Qi, Pi, M. Oops. Wait a minute, I'm helping with my pen. Okay. Okay. I don't have, all right. 1 second. Yeah. I times M P and T, and then la visibilidad symbol P T K, just to take the last one here. And for the exercise B, yeah, using this permutation with the basic vectors, we have that this C J is just C dot EJ, and this is just with this sheet here. 1 plus E2 plus E3, yeah, EJ, and at the end, this is just G, yeah, delta chronicle using these symbols here. It's just 1J plus connector delta 2J and plus 3J. Yes. Yeah. That's it. Okay. Do you have any comment related to these exercises? Please let me know. Oops. Or please write your questions in the chat, or just use the microphone. 1.4. Okay. This one? Okay. Yeah. This one. Yeah. That was a typo. Sorry. Yeah. 132. Okay. Thanks, ma'am. Yeah. Any other comment or question? For the next section, we're going to deal with some probability density function exercises. Yeah, as Professor Keynes mentioned, the POP, that book is very useful for this lecture. So if you have the opportunity to read it, yeah, that would be great. I'm pretty sure that you can find that book on the internet or download it elsewhere. But most of the lecture is based on what Professor Pop mentioned in this book. Statistics, turbulence, integral length scale, probability density function theory, modeling. This book is awesome, yeah, for following this lecture. Yeah. As Professor Andrea mentioned, yeah, it would be nice if you have some questions. Just try to activate your microphone and participate during the class. Otherwise, you won't have the opportunity to solve your questions directly with Professor Kemp. So this is a very nice opportunity for every section. If you have some questions related to this lecture, don't worry. So interrupt him or interrupt me. If you have any comment, just try to say I have a question, and immediately we will solve your queries related to this lecture. Because online to now, as far as I know, we don't have any tutorial, any section for solving our questions. So it would be nice if you use your microphone when you have a doubt or question about this topic. Okay, guys. If you don't have any other comment, I just gonna say thanks for your time and thanks for attention. I'll see you next week on Monday. Thank you. Bye. Thanks. Bye.